Okay, so today I'm happy to present Misha Kornev, who will tell us about material chromatography theory on the phonological side. Please, Misha, take it away.
Yeah, thank you. So we can start with some basic definitions about the category of phonological coarse spaces. So now suppose that X is a set, then consider the set of all subsets of X, P of X, the set of all subsets X. And we say that we have a chronology on X definition, a chronology on X is a subset of P of X, subset say B, of the set of all subsets, such that the first point that the unit of all B from B is a full X. The second condition is that if you have the fact that A is a subset of B in the chronology B, then it follows that A is also in B. And the last condition is that if you have, so you can form the unit, you can form this this set, and it should belong to the chronology B. So we will say that B is bounded. We will say B as the set of all bounded subsets. Bounded subsets. Also, the next bottom definition, we say that D is locally finite. or countable if for any B from the set B, the set B, the intersection between B and D is a finite or countable set. Okay, now now I want to define the following construction. So if you have a subset of the Cartesian squares of X, say U, use a subset of X times X, then we can form the following inverse object U inverse consisting of all pairs xy from x to x, such that the reversed pair belongs to the U, the set U. And also we can, if you have two subset of x times x, then you can form a so-called composition between these subsets, say U and U prime. Then we say that then we can form this as consistent of all points from x times x, such that there is z from x which connects some which connect to pairs, such that xz belongs to U, and also z y belongs to U prime. So some picture here looks like this. Informal, really. Okay. Now we define a core structure on a set X. So a coarse structure on X is a subset C of the set of all subsets of x times x, which is closed under the operations introduced above, so closed under the composition for forming unions, finite unions. Taken inverse, taken subsets, and also it should contain the diagonal of x, and C should contain a diagonal of x. Okay, so it means that more concretely, I can write it down as follows. This union should belong to C if each AI is in C, and also the composite shouldn't see, shouldn't see if it holds for AI and AJ, and also and if A1 is a subset of A2 is a subset of A1, and A1 in C, then it follows that A2 is in C, is also in C. Yeah. Okay. Okay. Good. now define the following notion, so-called U thickening of B of some bound set. If you have a subset of your if you have a subset of x times x and a subset of x, say you have U is a subset of x times x and B is a subset any subset any subset of x, then we say that we have a UB is the following set consisting of such x from x for which there exists B from B such that the pair consisting of x and B belongs to U, and it is called the U thickening of B. And we also say that the elements of a set C, the elements of C are entourage of X or entourage or controlled subsets. Controlled subsets. Okay. Now I'll give some. So I'll give more definitions. We say that the fact that we have a core structure means that we have a Bernoulli on the x times x plus some groupoidal-like properties. Coarse structure on x is the same as some Bernoulli on x times x plus groupoidal-like properties. Okay, so we have two structures on our set X. We have a Bernoulli and we have a core structure, and they should be compatible. And so we have our set X and a core structure C and some Bernoulli B, and we say that it is a Bernoullical core space if a core structure C and and the Bernoulli are compatible. It means that if for any controlled for any controlled for any control thickening controlled thickening of a bounded subset is again bounded. So take B a bounded subset and consider U of B, and in the case when U of B is again a bounded subset, then you are uncertain of saying of compatible structures or Bernoulli coarse space. So if you have the following situation, when you take any B from the set of bounded subsets, and for any U from X times X, you have the fact that U of B is again bounded, then we say that our Bernoulli and Coarse structure are compatible. Okay. Yeah, and now what about morphisms? So we should define, of course, objects, and now we're ready to define morphisms. We say that F is proper if for any B prime from B prime fancy F inverse image of B prime is in B. So you have a arrow from say XCB to X prime, C prime, B prime, and for this map, this map is called proper if for any bounded set B prime we have the property that the inverse image of B prime is in B. And we said that F is Bernoulli if for any B on B, just the image of B is in B prime. Okay. Now consider any map between sets with coarse structures. So suppose that have just a map between X and X prime, C prime, and we say that F is controlled if for any U from C, from our core structure, the following f times f of u is in C prime. So in this case we will say that f is controlled. And now a morphism between Bernoulli coarse spaces is called a morphism. In the case if f is controlled and proper. So the definition suppose that f is some map between sets x and x prime with chronological and core structures, then f is a map if it is a map between x and x prime such that f such that it is proper and controlled. And it means that Bernoulli coarse spaces form a small category. We will consider a few examples soon. Bernoulli coarse spaces form a small category born coarse. Okay, now it's time for examples. Examples. Okay.
May I ask a question?
Yeah.
Why is the category small?
The category is small in the usual sense, I guess.
Why?
Why? Why? Okay, just a second. This is a requirement, I think. So
okay, so we just bound the cardinality of the underlying sets then.
Yeah.
Okay, so
Thank you. Yeah, now some examples. So the first example. Now suppose that X is a set and consider some subset of the Cartesian square x times x, and we can form the following minimal coarse structure. We just take A and we and we look at the definition of the core structure. So we should have a subset of subsets of x times x, which closed under these operations. So and also we should have diagonal, and so we can take A and just consider completion, or I don't know, and also we add diagonal to our family of to our set, and then we will have a minimal core structure. So we just generate a minimal core structure by this set A. Minimal core structure. And for any W, the subset of X, we can form the minimal Bernoulli generated by W. So as in the previous case, let's look at the definition, and we just take our W, and what should we have? We should have all subsets of our set W, and yeah. Okay. Okay. Now we can. But we. Just a second. So we want to have the fact that the Bernoulli, this minimal Bernoulli and the minimal core structure are compatible, and why this is the case. So it is so. Consider any entourage U. U in A, any entourage. And so we consider so-called generates an entourage U in A, and generating bounded subset B in our W, generating bounded subset, and now we can form the following lignin U of B and U are reversed D, and these guys are contained infinite unions of members of W, contains infinite unions of members W. And it means that the Bernoulli be generated by W, and the core structure C of A, C generated by A, are compatible. Okay, the next example. The next example is about discrete Bernoulli coarse space. Discrete Bernoulli coarse spaces. So again, for any set X, consider a minimal core structure C, which is generated by the empty set. And in this case, of course, we should this resultant set should contain diagonal and all subsets of this diagonal. So we have a diagonal of X and all its subsets. C min has a diagonal of X and all its subsets. But by definition, for any Bernoulli structure, say B, this structure and the minimal core structure are compatible. It's obvious since if we form this U of B, it will consist of such B from B with B capital, such that there is a B the same B from B, such that B in B. Sorry, no, not in B, but in B, of course. Yeah, and it is the case as we have said. This U. We said that the diagonal is in our core structure. Yeah, and thus we have that. Of course, U of B consists of all B. In particular, so in particular, we can take as B the minimal Bernoulli structure. In particular, take B min consists of finite subsets of X, just all finite subsets of X. Okay. The next example. Consider a Coarse space. Then there exists a minimal comparable Bernoulli. A minimal compatible Bernoulli B, and it is unions of the subsets of X. It consists of the subsets of X which are bounded for some entourage of X. So in this case, we will say that B is generated by C. B is generated by C. So we should verify that our structures are compatible, but it is so, for example, for any V of B, of course, it is bounded since it is bounded for any V from C, since B times B is in V of B. Okay. The next example is in the next example we will define inverse image of structure. If you have if you have some structure and you have a map between sets X and X prime, say, then you can transfer your structure, sorry, pull back your structure, and suppose that X prime, C prime, and B prime is a chronological Coarse space. And you have a map between sets X and X prime, just a map of sets. Then define the following F star of C as core structure generated by the pre-images of f times f of u prime, where u prime lives in C prime. And also you can define, you can pull back the Bernoulli, and it will be generated by pre-images of all B prime, where B prime from B prime, of course. Then in this case, the map between chronological coarse spaces it is really a map between chronological coarse spaces. Oh, yeah. And we get a structure, the corresponding structure on the set X. Isomorphism in the category chronological coarse spaces. Okay, and the fact that it is really the desired structure can be verified by it's obvious. It's obviously it follows from the definition and the definition of the structure and the definition of the condition of compatibility. Okay. Now, the next example is crucial, is very important. So suppose that you have metric space. In this case, D can have infinite. Can you give infinite values? So you can have infinite distances between points in your metric space. Of course, it is a metric. The metric is some metric space. Okay, and now we can define the set of Bernoulli, just the Bernoulli. It will be generated by the following disks or balls. BD, it is just a ball. This is a ball centered at the point X with the radius R, and R runs R is a positive non-negative number, and X is a point in X. And define the entourage UR as consisting of such pairs XY from X times X, for each distance between x and y is less than r. And now verify some conditions from the definition. So we can form, of course, the composite, and it is obvious that we get this u with a subscript r1 plus r2. Just you have a point, say here x, and point here and here y and z, and the distance between these points is less than r1, and here r2, and by the triangle equality you get the desired property. And obviously we have that inverse u r1 is u r1. Also, if you have a union of ui's u rk, then it will be u with the maximum radius. Ri runs from 1 to k. Okay, and of course, if u is a subset of ur and ur and c, then we require that u and c, we require this fact. We require. Okay, and now the set of so the core structure is generated by this ur, by these entourages are from r is strictly a positive number, and yeah, it is the coarse structure. Okay. And now yeah. Yeah, consider the next example, which comes from the group theory. Yeah, and of course, this example is also such one. You can find this situation in, for example, group theory, or in the theory in Romanian. Riemannian manifold theory, for example, and this study can be applied in the case of studying Cayley, for example, Cayley graphs, or if you have some combinatorial groups and you can you wanna find some interesting properties, or you just wanna you just when you just want to study these different combinatorial groups, you can take their calligraph, and you can study some metric invariance of these spaces, and this is a motivation for this study of Bornological spaces, or and etc. So, and the following example gives an illustration of the application of this theory when we are talking about groups, or group category groups. So suppose that gamma is a group, and we can consider a minimal Bornological structure, the minimal Bornological structure on gamma, and one can consider the gamma invariant entourage. So consider subsets of B times B such that they are in gamma invariant under the action, the diagonal action, the gamma invariant entourage. So suppose that we take B from the set B min, and one can form the following canonical structure, canonical coarse structure C. It is generated by these gamma invariant entourages B cross B, where B is in B min. The canonical coarse structure. Yeah. Okay. Now. Yeah. Some remark. I wanna give some remark. In the case of a metric space, it turns out that it's suffices to consider the only one entourage that you can generate your entourage set, coarse set of courses, your coarse structure by the only one entourage U in the case of metric space. Yeah, this is some lemma. So if you have metric space, and we suppose that this metric space is a path metric space. Path metric space. It means that the distance between any two points is the length of a minimal path between x and y. So you have 2 points, x and y, and there is a path, and this path is a minimal, and the length of this path is the distance between these points, x and y. So for example, geodesic spaces or something like that. Yeah, and CD, in this case, CD.
I'm sorry, but what is a path in this context? Just a map from the segment, or is it?
Yeah, just a map from the segment to the space.
So, for example, when we consider Cayley graphs, do we consider them as CW complexes, or do we just consider them as metric spaces that coincide with the group itself?
Yeah. I think in this case we should use a word metric. Word metric.
Yeah, sure. But the question is, so we consider a Cayley graph as a CW complex, not as just some collection of points that correspond to elements of the group.
Yes, but I think that there is no problem. We just we can continuously we can continue this metric to our edges linearly, just.
Sure. My question was, do we do that or not? Because in one case, it seems that the space is not a path metric space because there are not enough points. And in the other, it is a path metric space.
There is no enough points. There are no enough points. Why so? We can take any 2 points, and so we can form a path between them. And what's the problem?
No. So never mind.
Probably you mean that the space would be large or not locally, but locally behaved.
Never mind. I just thought that maybe sometimes we consider like Cayley graphs, or I mean, a group with the word metric as just a collection of points without like any edges present, so it becomes disconnected, and we don't have. Well, it's not linearly connected, hence it can be path metric space. The confusion was in that, yes. But as you said, it's not very relevant. We can always extend the metric linearly on the edges. So,
okay. Okay, so suppose that CD is the associated core structure. Then there exists an entourage U in CD, which generates our CD. This can be verified easily. So if you have a so if you have 2 points x and y, then you can draw a path between them, and the distance will be finite, and you can subdivide it into small segments, small subsegments, and this pair is a root, can be considered as a root in this path, and it's obvious. Okay. Now I want to talk about yeah, I want to talk about products. So the category of biological coarse spaces has all non-empty products. The category biological coarse spaces has all non-empty products. For the case of the empty set, one has a fail, since there is no the terminal object in this category. So I'll meet this. I'll meet the proof. The following lemma said that this category has all coproducts. All coproducts. Okay. Now discuss the following hints, which can help to prove different statements. So if you have a biological core space XCB, and you have an entourage, say U, an entourage of X, then you can form the following phonological core space, in which we replace the core structure by the C generated by U, by the one generated by an entourage U. And this it is easy to see that our X is isomorphic to the colimit of XU, where we take colimits via the maps yeah, via the natural maps, natural induced maps. Okay. Now we're ready to establish homotopic category of this category, but no. At first, I give an example. So if you have two Bernoulli spaces, X, CB, and X prime, C prime, and B prime, then you can consider tensor product. So the tensor product is just a Cartesian product of everything. But for the usual product, it is not the case. So you have a functor. So you have an operation on Bernoulli coarse spaces, which gives you a structure of a symmetric monoidal, which gives you a symmetric monoidal structure on a Bernoulli coarse spaces, and with the units. Yes. Yeah. This operation gives monoidal symmetric monoidal structure on the category, on this category. Okay. Now we're ready to define some homotopical stuff. So consider our category of consisting of Bernoulli coarse spaces, and we can form a new category consisting of presheaves on this category, valued in the category of spaces. So we say that the category of spaces is the large presentable infinity category of small spaces. So you have a category presheaves on analogical coarse spaces. This is just functors from the Born course up to the category of spaces. So the large presentable infinity category of small spaces. Okay, and now our aim is to define some morphisms along which we will make some localizations, and so we will have two stages of localizations, as in the case of A1 homotopy theory. And after these stages, we will have homotopy theory of Bernoulli coarse spaces. But first of all, we will talk about descent. So we should define a Grothendieck topology on the category of monological coarse spaces and the category of infinity category of sheaves corresponding, of course. So tau chi. And to do this, we will start with the following definition. We say that Y is a big family on X. So yeah, this big family consists of subsets of X. This is a family of yi. Yi is a subset of X, such that for every I in I, and for any entourage U, there exists the index J such that your thickening will be in Yj. So this is a weird definition, but it is natural in the setting of the following example. So suppose that C is some coarse structure on C on X, sorry, a coarse structure on X, and now sorry. Consider some monological coarse space, so X, C, and B as usual, and in this case, the family of all bounded subsets is a big family. So this is a trivial example. In this case, B is a big family on X. So it is indeed you can consider this thickening, and by the compatibility requirement, of course, you should have the following condition, since your thickening should be a bounded subset, of course. Okay. Yeah. The next definition. This definition is about a complementary pair. So you have a complementary pair consisting of Z and a family of subsets of X with the such that there exists I such that Z and some yi is a whole set X for some I. Okay. Consider the example. So if you have a complementary pair, logical cross space, and the morphism, so you have morphism and pair Z ZY, then you can form you can pull back this structure, this structure on X, and you can pull back this to X prime. And the corresponding complementary pair will look like this: F inverse image of F of Z and inverse image of Y, just pointwise. Okay. And now we should define the family of weak equivalences. What are weak equivalences? So I should postpone it. Sorry, I should postpone it. But now we should define a growth-induced topology, and after that we can talk about sheaves, and after that, of course, we should define our structure. Yeah. So in this stage we have only pre-sheaves, and we should build sheaves, but for this purpose we should have a growth-induced topology. So I give some definitions. We say that so recall that one can think about the category of pre-sheaves on the category C as the category of functors which preserve limits from the category of pre-sheaves on C to the category of infinity categories. And also we can define the following composition between pre-sheaves. If E and F are pre-sheaves, then we can form a limit of E of X, where limit is over Yoneda embedding X to So over maps from unit of X to F in the over category, slice category C over F. And in particular, if F is a representable pre-sheaf, so if F is a uneda of X, then this is E of X, for example. And for a big family Y, one can form a uneda of this big family as the colimit of unedas of yi over I in I. So, and it belongs to pre-sheaves on chronological coarse spaces. Okay. And now the following definition, which is about the descent. So the definition of descent. So we said that a pre-sheaf E satisfies a descent for complementary pairs. For complementary pairs, if the value of E on the empty set is this final object, and for every complementary pair, you have the following diagram, square diagram, which should be a Cartesian square. So, and this we take an intersection, and it is a Cartesian square. A Cartesian square in the category of spaces. Okay, now the following lemma tells us about the fact that the Grothendieck topology, the Grothendieck topology tau chi such that all tau chi sheaves are exactly the pre-sheaves they are the pre-sheaves which satisfy this descent condition, which satisfy the this descent for complemented pairs. Yeah, and it can be done by the so I think yeah you can prove it, of course, but I think we skip it because we have no time. Yeah. But what I will prove, it is the following fact. So lemma tells us that Grothendieck topology, this Grothendieck topology, which exists by this lemma, tau chi on our category is subcanonical. So recall that subcanonical means that all representable pre-sheaves should be sheaves, subcanonical. So we should verify this fact. So consider some x prime, some object in the category of monological coarse spaces, and consider the representable pre-sheaf. Of course, it looks like Yoneda of x prime, and we should verify that it is indeed a sheaf. Okay, so first of all, we notice that this Yoneda of x prime can be factorized as in the following way. So we may consider only the set value pre-sheaves instead this general case. So we have the following composite from this is a category of sets, and it can be embedded to the category of simplicial sets by the nerve construction, and after that you have a composition. So you have a map to the category of spaces, and yeah, some iota, some map iota, and this Yoneda of x prime comes from some y of x prime, where y is a Yoneda from monological coarse spaces to the category of pre-sheaves, set valued pre-sheaves. So this is a usual Yoneda monological coarse spaces, and we just take post composition with this functor. So you just take your functor y, and after that you apply your functor iota. So iota, Yoneda of x prime is the composition between y and iota of x prime. Okay, and now we can note that this iota preserves limits, and so it suffices to consider the case of the set valued sheaf y of x prime in this category of set valued pre-sheaves on Born course. Okay, and in this case consider the complementary pair, some complementary pair. On logical coarse space X, and then we must show that this map. So yeah, this map pointwise over this right. This map is a bijection, so this is just this is just a condition that our square is a Cartesian square. But the fact that it is injective map follows from the fact that for any z we can find yi0 such that this union is whole x. And the interesting case is that is about surjectivity, and so okay, consider some element from the right hand side, and as we in the usual category of sets, then Cartesian square is a thing, is an understandable thing, and then it consists of morphism. So element of this guy consists of a morphism f from z to x prime, and compatible family of morphisms gi. So gi from yi to x prime, such that restrictions z, restrictions on the set z, on the intersection between z and yi coincide with the intersection restriction sorry of f. So this is just a compatibility. So okay, and thus we can glue these maps. So we define a map on the set z and on the set yi, and we can glue them together, and we can form the map H from whole x to x prime, such that H restricted to the z coincides with the f, and restricted to the yi coincides with the gi, respectively. And now one can verify that H is really a morphism born in the category of logical coarse spaces. But I think that we can skip this. And we are done. Yeah, but of course. Yeah, and we're done. So we just verify that this square is Cartesian, and it can be done easily, and I think that the details can be skipped. Okay, so we have no time, and I think that we next time I can continue my talk if you want, of course.
Well, of course, it would be great. Thank you for this exciting talk. Let's thank the speaker.
Thank you.
Are there any questions, suggestions, comments regarding this talk from any of the participants? Okay, if there are none, then let's thank the speaker again.